Hello, and today's learning targets are I can determine the number of solutions for a system, I can solve a system of equations by graphing, and using the substitution method. So we are going to review the unit on solving systems of equations. We will see two equations, and our goal will be to find the ordered pair where the lines intersect if they do. We will look at solving a system by graphing and solving with algebra, so by not using a graph. So the three possible solutions are that we could have exactly one solution, which is where the two lines that are graphed, where they would intersect. And where they intersect, that would be our one solution, and we'd write that as an ordered pair. We could have infinitely many solutions, so the two lines are actually the same line. Or we could have no solution in that the two lines are parallel or that they never touch or have the same slope. All right, so let's take a look at an example here. So we'll solve the system by graphing, and we'll tell how many solutions exist. So we're going to graph both of these lines here, and one of them will be red and one of them will be blue, and we'll see where the intersection is, if any. So I'm going to graph the red equation first, which means I'll graph my y-intercept of 3, then move according to the slope of up 2 units over 1. Go ahead and connect those points, make my line as straight as possible, and then I'll go down 5, then my slope is -2, so I can see here that the two lines intersect once, and where they intersect is the one solution, and that one solution is at -2, -1. Let's go ahead and look at a different type of setup on the next page. So now with this example, we are still going to do the same thing. We want to see if there's a solution, but now the examples are in standard form, which is ax plus by equals c. And to graph these, it might be easier to get them into slope-intercept form, which is y equals mx plus b. So if I rewrite this first equation, x minus y equals 2, and I want to get y equals, I'll subtract x to both sides and then divide everything by a negative, so y equals x minus 2. I'll go ahead and graph that equation and go down 2 units, up 1 over 1. Okay. And then with the second equation, I'll go ahead and let's rewrite that one as well. So subtract 2x, 3y equals -2x plus 9, divide by 3, so y equals -2/3 x plus 3. So I'll graph this equation as well, down 2 over 3. So it looks like these two lines also cross at one unique location, and that one location, as we can see that, as best we can with my drawing, would be 3, 1, and again there'd be one solution. Okay, now let's take a look here at the last example. Okay, so the first one is already actually in slope-intercept form, so let's go ahead and graph that and go down 6 units and then up 1 over 2 for the slope. And then with the second equation, I'm going to rewrite that into slope-intercept form so it's easier to graph. Let's fix this. Let's write this a little bit better. All right, so I get y equals 1/2 x minus 6. So as you can see, these are actually the same equation, right? So I mean, I will have the same graph. So I will have infinitely many solutions because the two are the same line. So now we know that a system of equations is two equations, and we want to find the point of intersection, or the solution. But now we are going to solve without using a graph and with using the substitution method. So what I'm going to do is, when I see this first example here, and again, so we don't have a graph, so what's another way to solve this system? Well, substitution method. So I'm going to take, I see I have y by itself here, and then an expression that equals y. So what I want to do is I want to take the expression that y equals, substitute it in where I see y in the next equation, and get rid of the variable y so that I only have to work with x's to solve. And then when I get my answer, I'll plug it back in and solve for the other variable. So what I get here when I substitute that back in is 3x plus, now here comes in the 2x plus 1 equals -9. So I'm just substituting in that expression for the variable. 5x plus 1 equals -9. We'll solve for x. So I get x equals -2, so now I'm going to plug that back in to whichever equation looks easiest, and the first equation looks easiest to me, so I'm going to plug it in for that one and get y equals 2 times -2 plus 1, so y equals -4 plus 1, so y equals -3. So my final answer is -2, -3. And I could check my work if I wanted to, and I could go ahead and plug in -2 for x and -3 for y into both of these equations, and it will hold true, and they will work out because they are a solution. All right, let's try another example. Again, when I see a variable equal to an expression, and a single variable here like y equals, this works really nicely. I could, if I did see x equals, I could also do that as well. It doesn't matter which variable I'm substituting in for. So here I get 2x plus -4x plus 12 equals 2. Combine my x's, -2x plus 12 equals 2. Subtract 12. Now I'll plug that back in, and I'm going to use that first equation again. That one looks a little bit easier to plug in the value for. So my final answer would be 5, -8. All right, I'll do one last one. We'll finish up with this last one on the notes here. Again, feel free to do the one above if you would like additional practice. I will post the answer to that problem when I'm done with this one. But I'm going to go ahead and, again, we'll use the substitution method. So now I have minus, I'm going to put parentheses around x minus 2 because I will have to distribute that -1. 3x minus x plus 2 equals 6. Combine my x's. X equals 2. Now I'm going to plug that back in for the second example, for the second equation, and 2 minus 2 is 0, so y equals 0. So my final answer is 2, 0. If you did take the opportunity to complete the problem above, the answer for that one is 1, -2. Thanks for listening to the review video on system of equations, and specifically the number of solutions to a system, solving by graphing, and solving by using the substitution method. We will continue our review on system of equations, but for now, have a great day. Bye-bye.